Hi, I'm Xenowave, and in this video I'm going to talk about synth fundamentals and what you can expect to see in most synthesizers. So first, what is synthesis? Synthesis is what happens when electricity is used to generate sound. A synthesizer is an electronic instrument that produces sounds using synthesis. A synth parameter is just something you can change inside of a synth, usually in the form of a button, a knob, a slider, so on. So for example, if I want to change the pitch of this saw wave, I just rotate that knob. In the context of synthesizers, an oscillator is what your synth uses to generate, control, and output waveforms. Your average oscillator allows you to control the waveform's pitch, phase, and amplitude in some way. Synths usually have two or more oscillators. So a really important concept to understand in sound design and synthesis in general is the idea of modulation. Modulation just means change, but there are many ways to modulate something. There are many ways to modulate in your average synthesizer. Modulation is usually achieved by using LFOs, envelopes, controller mapping, and velocity or keyboard tracking. Before we move on, keep in mind that oscillators don't have to go directly out to speakers. They can be used to control a parameter in a synth. This is called cross-modulation, which brings us to the LFO, which is just cross-modulation when the frequency of the waveform is so low we couldn't hear it anyways if a speaker were to output it. So let's put an LFO on the volume of the saw wave. I'm going to go over to my synthesizer's LFO section. We have volume, LFO, turn up the amplitude, and increase the frequency a little bit. Here's what it sounds like now. Versus before. I pulled up a totally different synth to show that even though methods of modulation in synthesizers may be designed differently, the concepts are fundamentally the same. So in this synthesizer, the LFO is more of a graph that you can customize and assign to any one of these knobs. So for example, if I'm messing with knobs, and I find that I like how it sounds when I change it, I can throw the LFO on there and do this. Or if I'm messing with the pitch of the sound and I like how that sounds, I will throw the LFO on there and just have fun with that. And of course down here, like rate for example is frequency. And amplitude and phase are just controlled directly in the graph, like this. I have an LFO on the volume of a saw wave on yet another synth, but to wrap it all up, the frequency of the LFO is how fast the parameter changes. The phase of the LFO controls the starting value of our parameter. And the amplitude of the LFO controls how intensely or how far the parameter changes. So right now we're at max intensity. If I bring it down, we'll barely hear a difference. You can see it up here though. And if you bring it down to 0, nothing. No change. By the way, the tempo button allows you to match your LFO with your project's tempo, and the global button just stops your LFO from restarting when you press a new note. You can expect to see those controls in just about any synth that has an LFO. Next we have envelopes, which is another common method of modulating parameters. Envelopes use a graph called the ADSR graph, which represents how a parameter changes over time. So what is ADSR? ADSR is just an acronym that stands for attack, decay, sustain, and release. I picked this synth in particular because I really like the way it visualizes ADSR. It's called Vital and it's free. I'll put a link in the description. So this is the envelope right here. It's on the volume of this saw wave. Also, before I forget, keep in mind that every ADSR control is measured in milliseconds except for the sustain control, which is just the parameter's value. Attack is how long the parameter takes to come in when the note is pressed. For example, I have the saw wave over here, and it has no attack. But if I increase the attack, we're going to hear the volume of the saw waves fade in. If I increase it more, and that's all the attack does. Decay is how long the parameter takes to fall to the sustain level of the envelope. Sustain is just the parameter's value after decaying. The parameter will stay at the sustained value until the note stops playing. For example, if I change just the decay, we won't hear a difference. It's when we change the sustain, we'll start to hear a difference. And then we can shorten it or lengthen it. And for sustain, it's stuck at this node right here when I hold the note. And that's how that works. And release is just how long it takes for the parameter to go away when the note stops playing. So now let's see the release in action. I'm going to adjust it so it's a little obvious. So now I'm going to hold the note for a little bit and then I'm going to release it. And that's basically how the release works. So here's what it sounds like with no release. Just an instant cutoff. And then a tiny release. Delay and hold aren't talked about as much, but I think they're worth noting. Delay is just how long it takes for the ADSR to begin modulating. So if I adjust it like that, if I press a note, it's going to be delayed by however many milliseconds this is. Hold is just how long the parameter stays at the attack level before decaying. So for example, I can use the hold knob to extend the amount of time it takes for the signal to hit the decay section. So let's bring the sustain down. So right now the hold is at 0, so the decay will happen instantly. But if I extend it, that's what happens. Controller mapping is whenever you set up a controller to modulate a parameter or a set of parameters. This is commonly used with automation, which is when you set your controller or parameter how you want it to modulate over time. For example, let's say I'm designing a sound for a melody. And let's say I like how that sounds when I turn this knob. So what I can do is just map this to a controller. This synth allows us to quickly map to a controller, so I'm going to choose mod X. And now if I come down here, I can control the pluck with mod X. And you can see how it's mapped right here. Now I could just automate just the pluck knob, but the problem is that it's just the pluck knob. What's awesome about mapping to controllers is that you can map whatever parameters you want to it, which can result in really robust and complex sounds. Or mess. That's really dependent on the skill of the user. So now let's just automate modulation X. And we're just going to do that. And now we're going to have the pluck come up as this plays. In some synthesizers like Serum, PhasePlant, Massive, etc., the controllers are called macros. So right now I have macro 1, and I'm just going to assign it to, I'll try the sense. I'm just going to do that. And now when I control this macro, the pitch will change. And the cool thing is, again, I can assign it to multiple things. So I'm going to bring the level down and then do that. Now it's controlling both the amplitude and the pitch of this saw wave. One last thing about mapping to controllers is that some synths give you more control on how you map your controller over others. For example, since controller mapping is represented using a graph, we can just freely change this graph as needed. But in something like PhasePlant, as I've shown before, at least at the surface level, I can't think of a way to possibly replicate that. But to be fair, I don't know PhasePlant as well as some of the other synths. Keyboard tracking is when the parameter that you're modulating changes based on the pitch of the note that you're playing. Let's say I want to modulate the volume of this sound using keyboard mapping. So I'm going to go down to keyboard mapping and make this graph. And basically what this means is that higher notes will have higher volume and lower notes will have lower volume. Let me exaggerate a bit. And if I flip it, and that's the idea. Velocity tracking is when the parameter you're modulating changes based on the volume of the note you're playing. So let's say I'm messing with this knob and I want to map it to velocity. What I would do is just right click, quick map to velocity, and now we can see that this line right here is where our prism knob value is. So if I want to change that, I need to go to my piano roll and mess with the velocities. And the velocities are right here. And now we should see the value jump around. Just like that. So those are some basic methods of modulation. I highly suggest you look up the manual of your synthesizer of choice and learn how these methods of modulation are implemented so there's less frustration and confusion when you experiment. The manuals for all of these synths will be in the description. Now let's get into filters. A filter is an effect that changes the amplitude of a range of frequencies in some sound. The range of frequencies in a filter is called a frequency band. There are many types of filters, and I'll explain the most common ones using this tool called an EQ, which is basically a bank of filters. Before we go over the types of filters, let's go over the controls you can expect in your average filter. The first control we'll go over is filter cutoff. The filter cutoff is just what frequency the filter affects the sound. Next is the filter gain. The filter gain is just the amplitude of the filter at the cutoff frequency. Filter resonance is how intense the filter affects the frequencies at or around the cutoff. Filter order is how steep the frequency band is. This is a spectrogram, which is a tool that allows you to visualize the frequency spectrum over time. You can use it to reverse engineer any sound. The x-axis is time, and the y-axis is frequency. We'll be using this to look at how filters affect the frequencies of a sound. First, we have the low-pass filter, which only lets the frequencies below the cutoff point pass. So here's what it sounds like right now. And when I mess with the cutoff, when I add resonance, and when I mess with the order. Here's a steep order, and here is a gentle order. There are some filters that don't have a gain option, and the low-pass filter is one of them. The high-pass filter only lets the frequencies above the cutoff pass. Here's what it sounds like when I sweep the cutoff, and then add resonance, or take away resonance. and then steep order with resonance, and then gentle order, and again, there's no gain option. The bandpass filter only lets the frequencies inside of the frequency band pass. Here's what it sounds like. And then when I sweep the cutoff, and then increase resonance, decrease resonance, and mess with the order. So here's steep, and here's gentle, which is the same. And there's no gain option for bandpass filters. The bandstop filter only lets the frequencies outside of the frequency band pass. Here's what it sounds like. And then when I sweep it around, mess with the resonance, and then mess with order, steep order, and then gentle order, which also appears to be the same as steep. There is no gain option for bandstop filters. Peak filters let all frequencies pass, but they can increase or decrease the amplitude of the frequencies in its frequency band. Here's the peak filter. First, let's increase its amplitude, and let's mess around with it. So when I sweep the cutoff, it sounds like this. And then decrease resonance. Max resonance. And let's actually decrease amplitude. And then mess with the order. So here's a steep order. And here's a gentle order. The high shelf filter lets all frequencies pass, but they can increase or decrease the amplitude of the frequencies above the cutoff. Here's the high shelf filter. Let's bring the amplitude up first, and let's mess with the cutoff. Let's bring resonance down, and then up. And let's bring this all the way down now. And let's have a steep order. And let's get a gentle order. The low shelf filter lets all frequencies pass, but they can increase or decrease the amplitude of the frequencies below the cutoff. Here's the low shelf filter. Let's bring the amplitude up, and let's mess with the cutoff. And then here's no resonance. And then max resonance. And then let's bring it down. Here's steep order. And here's gentle order. Keep in mind, there are even more filters, but the ones I just went over are the ones you can expect in your average synthesizer. These other filters are so special, they're usually made into their own effects, which brings us to effects. I feel like it's important to go over the basics of how effects, routing, and the mixer works before coming back to synthesizers. The logic and concepts are all the same, it's just the design, workflow, and options that vary. With that being said, let's go over those basics. So first, a mixer is a tool that can process, route, and output sounds. Effects are tools that are used to process or modify a sound. A dry signal does not have effects on it, and a wet signal does have effects on it. Alright, So now let's get into some commonly used effects like EQ, compression, reverb, etc., and what they sound like when applied. Let me just quickly route all of these to the mixer. There we go. In your average mixer, you can assign your synth or audio to what we call a mixer track. When assigned, you can then control that signal's volume, panning, routing, etc. And of course, you can add in effects. So let's add an EQ into Vital's mixer track. An EQ is an effect that can shape or sculpt a sound by changing the volume of frequencies in that sound. For example, let's say I want less high frequencies and more low frequencies. So I would use this high shelf and just bring it down wherever I want and put this low shelf up. And here's my sound. Or if I don't like a particular frequency, I could use this peak filter and bring it all the way down, or a bandstop filter. And I could really surgically remove a specific frequency or range of frequencies. Reverb is an effect that adds space and stereo width to a sound by simulating sound waves bouncing off of surfaces in a room. Here's what reverb sounds like. A cool thing you can do with reverb is generate ambience by taking out your dry signal and maybe increasing your decay time a bit. And here's what that sounds like. And let's listen to the original signal. Huge difference. Delay is an effect that can add space and stereo width to a sound by echoing copies of the signal milliseconds apart from each other. Here's what delay sounds like. So the main control is time, which is just how long it takes for the sound to echo. So if I decrease this, it'll be faster. And if I increase it, it'll be slower. In the feedback section of a delay, you can control how the echo fades away. So for example, if I were to decrease the feedback level, then the echo would fade away more intensely, like this, as opposed to this. Chorus is an effect that adds depth/thickness and stereo width to a sound by playing multiple copies of that sound within 5 to 30 milliseconds of each other. This is what chorus sounds like. Choruses use LFOs to control the delays within the sound. If I turn the frequencies of all these LFOs down, we're not going to hear any movement. So it doesn't matter what I change the depth to. I would have to manually change it to get some movement. But as soon as I turn an LFO on, we start to get some stuff. A flanger is an effect that can add depth, movement, and stereo width to a sound by delaying the signal with a copy of itself, up to about 20 milliseconds. Here's what a flanger sounds like. The main differences between the chorus and flanger effects is that choruses delay the signal with multiple copies of the sound, and flangers focus on one copy of the sound, which results in a more prominent phasing sound. On top of that, flangers tend to have shorter delay times than choruses. Just like chorus, if I make the rate 0, I can control the movement with depth. The comb filter is a special type of filter that has multiple frequency bands. Comb filters can be formed by delaying a signal with itself, or they can be formed using a series of peak filters, bandpass filters, or others. This comb filter uses a delay, and this is what it sounds like. feedback controls the feedback of the delay, and frequency controls how fast the delay is. The all-pass filter is a special type of filter that rotates the phase of a signal, which lets the user control which frequencies are getting phase cancelled when playing together with the dry signal. Here's what the all-pass filter sounds like. So in filter 1, the filter is turned off, it's just the dry signal, and filter 2 has the all-pass filter, which phase cancels. Just to be clear, I'm going to turn off filter 1, and we're going to see that there's no change when I change the cutoff. The phaser is an effect that can add depth and movement to a sound by using an all-pass filter or a series of all-pass filters. Here's what a phaser sounds like. Phasers are controlled by LFOs, which makes the controls pretty similar to flangers and chorus effects. So if I were to change the minimum def, it would sound like this. And if I were to change the sweep frequency, which is just the frequency of the LFO, it would sound like this. Before I go over the next effect, I need to define what dynamic range is. Dynamic range is the distance between the loudest and quietest parts of a sound. With that being said, let's go over compression. Compression is an effect that uses volume automation in order to control a sound's dynamic range over time. So I have this vocal sample here.
House music.
And I want to make it so that the words house and music are closer together in volume. I can use compression to make that happen. The first thing I'm going to do is find out how loud the quietest part is. So I'm going to go over here.
Music. Music. Music.
It's about,
music.
let's just say, -15. So I'm going to make this threshold -15 decibels. Now the compressor turns on whenever the signal goes past -15 decibels. The attack parameter controls how long it takes for the compressor to come in after the signal crosses the threshold. So to make the compressor turn on instantly after crossing the threshold, I'm just going to make this 0 milliseconds. Now I'm going to adjust the ratio, which is how intense the compression will be. Right now it's at 1:1, which means that the input signal is just as loud as the output signal. I'm going to make it 2:1, which means that when the input signal increases by 2 decibels, the output of the compressed signal only increases by 1 decibel. The release knob controls how long it takes for the compressor to stop compressing when the input signal goes below the threshold. The gain knob controls the volume of the compressed signal, so if I want to make it quieter overall, I would just bring it down.
Music. House music.
Or if I want to bring it up, I can just do that.
Music. House music.
And this knob just controls different compressor algorithms. So I'm going to bring the gain up just a little bit. And I'm going to render this out. So here's our compressed signal and here's our original signal. So we can see that the dynamic range is much closer.
House music.
For extra clarity, if I want to compress even harder, I would just increase the ratio. So let's make it, like 6:1. And let's render this out again. So now here's our new render compared to our previous render. And now it's basically even. Here's what it sounds like.
House music.
And again, if I want to make my result louder, I would just bring the gain up. huge difference between the original sample
House music.
versus,
House music.
and that's compression. Distortion is when the shape of a waveform changes. The waveshaper is an effect that distorts sound by mapping the input signal to the output signal. So let's see what happens when I compress a sine wave too much. So I'm going to bring the attack down all the way and the release down all the way. And let's see where the threshold should be. Like, let's just put it at -20 and increase the ratio to a high sort of ratio. And that's what happens. Let's just make it louder. We can see that there's more harmonics here now. This is the waveshaper. The x-axis is input and the y-axis is output. So let's play with this for a little bit. This knob right here is our pregain, which just controls the input. This line right here. This knob is the dry wet, and this knob is just how loud the sound is after distortion. Here's an example that really helped me understand waveshapers when I was first learning them. So I have my sine wave right here, and I'm going to make a stair pattern. And with the stair pattern, we're going to see how it imprints onto our sine wave. So let's check it out. And that's what a waveshaper does. So that whole section I just did on effects is what we call post-processing, which is when a sound is processed outside of its generator. The effects chain is a set of effects that processes your sound. The order of the effects in the chain is the order in which your sound is processed. For example, if I put a distortion, a low-pass filter, and a comb filter, then the signal will get distorted first, and then low-passed second, and then combed last. Here's what that sounds like. If I flip the low pass and the distortion like this, then now our signal is getting low passed first, and then distorted, and then combed. And here's what that sounds like. What I just explained is what we call serial processing or serialization, which is when a sound is processed sequentially. Parallel processing is when multiple sounds are processed at the same time. For example, if I want to process this sound in parallel, I would route this signal to a different mixer track. And in this mixer track, I would add in whatever effects I want. So let's just add in reverb. And so now when I play the sounds together, I'm going to get this original sound and then this sound with reverb. And there's a reverb right there. Let's exaggerate. However, if I say get rid of the master and only have this routed here and this signal goes to the master, we're back to serial processing. Everything I had just gone over in the mixture applies to synthesizers. You can expect some combination of these effects in your average synth. In my experience, the most common effects I've seen in synthesizers are EQ, reverb, chorus, delay, and distortion. I will have a whole video on FX and post-processing. I just figured I should briefly go over this now so you're not left in the dark when it comes to your synthesizer's effects section. Like over here we have chorus, compressor, delay, distortion, etc. Or in this synth, the effects are reverb and some variations, flanger, chorus, phaser, delay, and so on. Or in this synth, there's overdrive, which is a type of distortion, tube amp, another distortion, and so on. EQs, filters, phasers, and so on. So if your synth has an effects section, it can probably route and process your sounds in serial and or parallel, all within the synth itself, which allows for even more modulation to form a sound. Unison is what your synth uses to generate copies of your output. These copies are called voices. Unison is commonly used to affect the pitch, phase, volume, or panning of a voice. I'm just going to add unison to the saw wave and explain what's happening as I do it. So first, here's what it sounds like. And the first thing I'm going to do is add in about 7 voices of unison right here. And here's what that sounds like. That sound is what we call a supersaw. So what's happening here is that 7 saw waves are playing at the same time at a 20% unison detune, which is basically how out of tune each voice is from each other. If I bring this 20% down to 0, we're not going to hear any detune. But if I bring it to 100%, we're going to hear all the detune, which is too much. So it's good to make sure your detune and other parameters are exactly where you want them to be. This controls the phase randomization of all the saw waves or voices in your unison. So if I bring this all the way down to 0, it means that all the phases are aligned and we're going to get this unique effect. Here's what that sounds like. This set of lines right here controls the distribution of our voices. So if I bring it up to +5, it'll sound like this. Or if I bring it down to -5, it'll sound like this. And let's bring the phase back to normal. So it's pretty subtle, but it makes a difference in your sound design. So that's a very basic look into unison. Let's turn this sound into a stab or something. The easiest method I can think of for making a stab is by putting a fast decaying envelope with no attack on the cutoff of a low pass filter. So what I'm going to do now is make sure oscillator 1 is routed to whatever filter I want. So in this case, filter 1. And I'm going to turn on filter 1, which is already a low pass filter. And I'm going to go over to envelope 2, drag it over to the cutoff of filter 1, like that. And I'm just going to mess with this envelope. Give it a fast decay, like that. And we should get something stabby. And I'm going to adjust the intensity of our envelope now. And there's your basic stab. If you want a bit of a cleaner sound, I would suggest putting the same envelope on the volume of your oscillator. Bring down the actual volume and you bring up the amount you want to modulate, and it'll sound like this. So now let's add effects like delay, for example. So I'm going to go over to the effects section, turn on delay, and I'm just going to mess with this. So first I'm going to make it tempo dotted and just mess with this. Cool. Now I'm going to add in reverb and mess with that. and there's a cool stab you can use in a song or something. So what you can expect in your Avid synthesizer is some combination of oscillators, unison controls, envelopes, LFOs, controller mapping, velocity tracking, keyboard tracking, effects, and maybe some routing options. Every synthesizer processes its signal in an order, and some let you change the order by allowing you to change the routing in the synth. In my experience, the most common order is this: oscillator voices, your methods of modulation, so LFOs, envelopes, tracking, mapping, etc., and then your filter section, your effects chain, and then output, and then, post-processing, whatever after that. It's important to keep track of your synthesizer signal flow so you know what's happening to your sound and when it is happening. Okay, let's say you like the sound that you've made and you want to keep it. This is where presets come in. A preset is basically just a sound that you can load into your synth. So in this case, for Vital, I'm going to right click in the middle, not on the arrows, it'll switch. And I'm just going to save it as this. And it's saved. Now, if I switch over, I have my sine wave preset, and I have my stab. And that's pretty much it. Make it a habit to save and organize your presets as you're sound designing. Your future self will thank you. Anyways, that's all I have for this video. If you have any questions, please let me know, and have an awesome day.